George, thank you very much for this invitation, and thanks to the department, to Kate, for this as well. It was actually very exciting to come after such a presentation of how important this sort of area of research is. I am in computer science, and I generally work on wearable systems, how to make them more efficient, more effective in what they sense about our daily life, especially for health, and how we analyze the data comes out, which is quite peculiar, quite unique for many characteristics. There's more on my webpage. I will be very specific on what I talk about today, but in general, I'm interested in things, behaviors, human behaviors that are difficult to sense. So examples of this are, for example, that we often need to understand continuous inputs for our better understanding. So sometimes you go to a doctor, once a week to get reading, but sensors can give you a continuous reading of that, perhaps. And perhaps we have commodity devices that can help there. Perhaps there's something that requires the user input and attention, and this is often not easy to get. And so we need proxy devices that can get that automatically. Or maybe the sensing that we have devised at this point is expensive or inaccurate, and we can try to do better. Or maybe it's invasive and dangerous. The first thing, just after hearing the previous presentation, I couldn't help by sneaking in one more slide about one thing I will not talk about today. But this is, if you want to hear more about this COVID-specific mobile phone developed application that uses sound. So we ask people to cough and breathe and read. So we record voice, then we analyze this data and trying to understand if we can have quick diagnostic respiratory tools using machine learning. I will not talk about that because I thought for this simple, but you can ask me questions later. For this particular symposium, there's another line of our research that is perhaps a bit more fitting. And you will tell me at the end if I'm right. So we are working in the area of next generation devices, what commodity devices people will wear, what kind of sensing you can implement on these devices, and what kind of sensors that are already there, what kind of things we can make the sensors that are already there do, how efficiently, how effectively, and what the data can do. This is a particular example of one device we've been working on, which are Earable. Earables are foreseen to become market leaders. So someone has defined them as the next smartphone. They will probably become standalone. They will probably have cellular connection. They will probably be more powerful, but they have a form factor, and they have issues with energy, clearly, and the kind of sensors you can put in these things. But they have interesting advantages related to where they are now in our body. So earables are on our head, which often is quite stable with respect to what you might want to measure. And I'll talk a bit more about that. Examples of other devices that have been used to measure activities or physiological characteristics are in points of the body that are more prone to movement and to be, offer a different kind of perspective. Also, you have generally two of these earables on your head. And we are interested in also seeing not just what we can do with devices like that, what kind of sensors could be put in there and how we can use it, but also how much we can put on the device itself. This is important because, well, the elephant in the room here is privacy of your data. And I often answer this from the systems perspective. And so I'm a systems researcher. And so I think from a system perspective, there is no reason why we can't keep the data close to the users and trying to put as much computation as logic as close to the user. This is something the industry is kind of starting to absorb as an idea, but there are systems challenges trying to do, especially doing it at this level, doing it with such a small device that has a small part of issues. So for the next 10 minutes, maybe, I will concentrate on one specific paper, which you can find on my webpage, you can find on archive, and then I'll reflect over this general area a little bit. So the general idea here is that if you try to measure general activity. So here you see in all the columns, at the top of the column, see walk, run, drink, chew, still, tap, tap, tap. So these are examples of activities that we would do. If you try to measure these using an accelerometer on your head, let's say in a earbud, you will see some sort of noise generated by head motion. So the first two rows indicate the activity and the signal, the pattern of the signal that you can see when the individual is not moving the head. And the second row indicates the activity pattern when the person is moving the head. As you can see, there's a big difference. The third and fourth row indicate the same, but with an outer ear microphone. So this sort of earable, I'm wearing some already, have an outer facing microphone. Many of them have it. However, if you try to use that, because of the kind of activity and things happening, the outer ear microphone is also not very good at detecting these activities. So the idea of what we try to see, and this is just one specific technical contribution, is that we've tried to look at the inner microphone. So the microphone that is in some earable, and this is an example of one, that the stays is inward facing towards the body, and see what we can do with that microphone, what we can detect, and how much we can then perhaps also look at the system's perspective when I get to it at the end. So the idea here is that this earable have a plug in front that creates an occlusion effect. And by when people move and are active, there's the vibration of their activity, so that their walking is propagated by bone conductivity in our body, and the plug-in, the occlusion effect makes that these waves are kind of the low frequencies of these activities are amplified inside the ear. And so if you have a microphone there, you might be able to hear things better. That's roughly, if you just want to listen to me for 1 minute, this is what you need to listen to. And so based on this idea, we have tried to see how much we could detect activities based on just the inner facing microphone. And as you can see, these are the two rows that you saw before, but these are the inner facing microphone. And there is no difference if someone moves the head, because that is completely not affected. That kind of activity of the head is not affecting what the inner facing microphone is. I guess if I had to ask myself a question at this point would be, yeah, but maybe with an accelerometer you could correct the signal, you could do some modifications. Yes, that's absolutely true. You can use post-processing to improve the activity recognition, even if the head is moving. However, this kind of study we've done is one that kinds of want to say, why not? What can we do? What boundaries can we push with this other sensor that is already there? And often from what we hear, smaller form factor earables tend not to want to put in another sensor such as an accelerometer if they can avoid to do that. So yeah, so that's why perhaps studying this is important. Now, because all the earables available have don't have APIs, we couldn't really tap into the raw signal. We built our own little random prototype, and I'm horrified by the idea of showing this to engineers. So I'm sure you're all giggling and laughing, but we did this to collect some data. And so here is an example of the signal that while someone is walking, you can get from the various earables so the earables are right and left, and the in-ear microphone. So so if someone is walking, you can see the steady movement, and you can see it in the signal quite clearly. And at the end, you would tap. In the interest of time, I will not show you that part. This is also, I've talked a lot about activity, but there is also one side of it, which is related to other things that this sort of inner microphone might be able to do. And one simple thing we've already analyzed is sorry, is gesture recognition. So if you're tapping on various parts of your head, what can you see? And this is researcher Dong demonstrating the various signals, and then I'll give you some examples on how we can distinguish it with analysis. So the things we have already tried are step counting, activity recognition, gesture recognition, and we do a sort of machine learning analysis of the data not in real time. Of course, we take the data and then analyze it, but clearly there is a potential of doing it on device, and I'll give you some numbers for that on our initial prototype. So we have done various studies related to step counting. One thing I haven't yet said is clearly, what if you wear different types of shoes? What if you are on different floors? If you look into the paper, we have tried to look at these scenarios as much as we could to see the differences. The result is that generally this doesn't impact that much. We can still detect the activities, we can still detect the step counting. Gesture recognition, we tried 12 gestures on the face. Of course, if you try to group the gesture in different parts of the area of the face, it's easier to recognize them. So 12 is probably too much, but if you get down to 5 gestures that you can do on the face just to give signals perhaps to that is even better. And these are some comparison of performance of SC is step counting, AR is activity recognition, GR is gesture recognition. Accelerometer is the first couple of rows, then the external microphone, then the internal microphone without movement and also with music, because we thought that might be affecting, and in fact there is some sort of effect. As you can see, the performance are quite good for the microphone. These are performance for all of the 12 gestures, so they are perhaps a little bit less than the higher ones that are for the activity recognition. We are over 90. For the gesture recognition, we are lower, but this is due to the fact that we have 12 gestures there that we're considering. I'm looking at the time. I still have a few minutes and I can present a little bit of our analysis. So by looking at different floors, we see that some of the activities and some of the floors, someone chewing while on carpet and left and right ear, but have some effect. But if you look at the scale, don't get confused by the fact that the scale on the y-axis is already very, very high. And so the difference is not particularly significant. One thing that I really would like to explain is this. So first graph just says, if I use data from both earables, because I have 2 channels essentially, then it's better. So so the third histogram, this part here says that when I fuse the data, it's better. Here is the performance per subject. So if I build this general model without considering the user, so the specific users, for some users, it would perform better than others. So let's look at user 2. So here, the orange and the light blue line are very low. So for this particular user is not working very well until we add some data from them. In other words, this user is kind of his activities are slightly different. So we need some data from the user itself, some personalization to make the model work better. But this is acceptable because just with 10 personal samples, which are easily gotten in a few seconds. Sometimes I remember to train a magnetometer on Google Maps, you had to do a figure of 8 with your phone some time ago. I think Google now has improved that, but that kind of training is an interesting thing that one might want to put it an example. With 1 minute to go, I will skip, I will go to the system considerations. We have tried to see how much would it cost in terms of powers, in terms of delay or latency, if we try to put the analysis of this on device. So if we were to want to do the analysis of the activity on device, And essentially, even with a prototype, and you've seen how bad our prototype is, even getting that sort of data and trying to use a not very optimized Raspberry Pi plus a microphone record, something very simple, we get reasonable power performance and a latency that is already less than 50 milliseconds, which is reasonably acceptable. The most of the latency is due, of course, to inference and to feature extraction. So I'll just go to this slide and finish here. Power consumptions, yes, we can do better audio chips and dedicated PCB. This can be improved, and I'm sure, guys, you will tell me all about this. Some issues with the fact that if you're using it in the microphone, you need to create this vacuum effect. So some might say, well, what if you need to hear outside? Well, obviously, this has been solved by the community by having some sort of transparency mode. It's possible to still have this occlusion effect, but avoid that you don't hear. So you can do both things at the same time. And we are working with some PhD students. I think one is, in fact, in the room on what other physiological signals we can do from earables, and in particular from in-ear microphones. And with that, I would like to thank, this is work that we're doing together. This particular work has been doing with Nokia Bell Labs support and with my ERC grant support. And Dogma and Raffaellini are actually the authors of this marvelous little work on in-ear microphone sensing. George.
Cecilia, thank you very much. Very exciting talk, super interesting. We already have a question. And may I ask people to post their questions on the chat, please? Thank you. Have you explored using EEG in the ear canal? Is it in the plan? That's the question.
Well, I know George is an expert on that, but we haven't explored this. I think it's an interesting additional sensor. We are looking at PPG to see how much can be done with PPG, and the accuracy at the moment of PPG is probably not marvelous. So that's definitely one thing. But EEG, obviously, many people are producing wonderful sensors. So putting it into the framework and trying to see what can be done is definitely very interesting. We haven't done anything in that.
Great, thank you. Any more questions? Is there anyone who would like to unmute themselves and ask a question? Yes, Dean.
Cecilia, if I can ask about the comfort and sort of what kind of duration of how long would I be expected to wear this, and is it plausible that I might be wearing it sort of 24/7?
So the earphones I am wearing have that occlusion effect, right? These are the, I don't want to advertise, but some types of earphones on the market already have that quality. It's already out there. I personally wear them for most of my day. And I think it needs the transparency, the things I was hinting at the end, needs to get better, because when I have this on and my daughter calls me from the other room, sometimes I don't hear her and I don't like that. So I would like both. There is a way to take the noise cancelling completely off. I don't want to do that either. So there needs to be smart ways of considering someone important is calling you. We need to adapt dynamically what you can hear from outside. But comfort is something, I am not an expert, I haven't built this sort of thing, so I don't work on that, but it's very important. People are building some earables for sleep monitoring. So the idea of comfort is becoming pivotal in this sort of commodity devices and in industry. So yeah, definitely it's something that needs to be looked at. But there's a lot of physiological signal that I think could be taken from the head and from the ear.
Great. Thank you. Let's thank Cecilia again. In the interest of time, if there are any further questions, please post them on the chat. Thank you very much.